All right, so I'm Szepieniec. I did my PhD here at KU Leuven, but in the meantime I started working for Nervos. Although I'm still a free researcher here, so the KU Leuven stuff is not out of place. I'll be talking about quantum computation and its effect on cryptography. So let's start with an introduction. Quantum computers are really, really cool. They use the tiniest pieces of the universe you can possibly find to do computation. And that's cool if you want to figure out what the universe looks like or how it operates. And that's actually also useful if you want to generate pharmaceuticals or nanomaterials or circuits. And actually, if you have quantum computers to compute circuits, you can use those quantum computers to compute better circuits for more quantum computers. So if we have a couple of steps in that direction, very likely we will have a boatload of steps in that direction. We can also use quantum computers to break cryptography, and we don't use quantum computers to prove cryptography, but we need to think like the attacker who has a quantum computer. And we can also use quantum computers to do cryptography. In addition to cryptography and science, there's optimization. Well, this is technically also science. And big data is not a suitable target for quantum stuff, because you need to send all this data into a quantum computer which operates at 0.3 Kelvin, and transmitting all that data takes a while. And that's why finance is sort of a gray area, because a lot of it has to do with processing big data. But sometimes there are interesting financial problems that don't take a lot of data to describe, but that are still very hard to compute. And that's exactly where quantum computers are excellent. And in case you think that quantum computers will make the blockchain so much more cool and powerful, the answer is no. They won't. And there's actually a very good reason for that. It's called the no cloning theorem, meaning that you cannot clone an unknown quantum state. And you can actually use that fundamental property of nature to generate money or identity, whatever you like. And once you have that, then you don't need a blockchain anymore for cryptographic money. So in general, quantum computers are not very good at solving NP-complete problems. But if you have a problem with some kind of structure in there, then it's likely that quantum computers, or plausible at least, that quantum computers do have a very large speed up. So in general, when do quantum computers stand a chance to provide a speed up? It's when your problem description is small, but it's still a very hard problem. And I guess I should add here, if the problem has structure, that's when quantum computers are really good. So my field is breaking and proving crypto in the context of quantum computers. I guess I could expand to doing crypto, but well, I prefer my cryptography to run on today's classical hardware. So what is the effect? Hang on, taking a look at these industrial applications, it should be obvious that quantum computers are coming even without the selling point of being able to break crypto, because we can generate fantastic pharmaceuticals and new materials and stuff. There is an industrial demand driving the construction of quantum computers. The side effect of this evolution is, of course, that quantum computers will break some crypto. Which crypto exactly? Mostly public key cryptography, and mostly RSA, or anything that relies on integer factorization, the discrete logarithm, elliptic curves, are not safe against quantum computers unless you're talking specifically about isogenies, but, well, most people wouldn't categorize that under the label ECC to begin with. Symmetric crypto seems barely affected. There is an algorithm, a quantum algorithm that you can use to attack symmetric crypto stuff, but it doesn't really perform well, and if you just increase the output or the key size by a couple of bits, then it's probably fine. And also, it turns out that some security proofs just are invalid if you have to take into account an adversary in possession of a quantum computer. Because a lot of these security proofs assume, implicitly or explicitly, that the adversary is classical. So if you want to develop cryptography that is resistant against quantum computers, you need to have a hard problem that's different from these, and you need to have a proof that explicitly takes into account the fact that your adversary might be a quantum computer. So you need to look at both elements. Post-quantum cryptography is the branch of cryptography doing exactly that. NIST, the US National Institute of Standards and Technology, is running a project at the end of which they will issue a portfolio of suitable crypto systems for exactly this purpose. There are two quantum algorithms that are very important to take into account here, and I will treat them in my presentation. The first is Shor's algorithm, which breaks both the integer factorization problem on which RSA is based and the discrete logarithm problem upon which Diffie-Hellman and most elliptic curve cryptography is based. Then there's Grover's algorithm, which is a generic search algorithm, and it's the quantum analog of exhaustive search, except it's a bit faster. So if you want to learn more about quantum computing, first you open the Bible, which is written by Nielsen and Chuang, of course. This is the book that every crypto paper that mentions quantum computing always refers to, and it really is an excellent resource, very accessible. It really demystifies what was previously black magic. But in case you're not religious, there's also poetry in the form of these lecture notes by Scott Aronson, and I really do mean poetry because it's really, really fun to read, and there are only a handful of formulas in there, so you could, in principle, give it to your 5th grader son or daughter, and they might even, probably would even like it. And then there's the Zoo once again by NIST, or NIST compiled this once again, and it's just a collection of algorithms that are known to be faster on quantum computers, or where quantum computers are known to offer an advantage. More traditional lecture notes, I can recommend Preskel's lecture notes and the Wolff's lecture notes here. All this information is in my slides anyway, so don't bother copying it down from here. So that was the introduction. Now let's see how to think about quantum computation. And I'll take the same approach as the Bible takes. I'll talk about the postulates first. So whenever you have a collection of the tiniest pieces the universe can offer, the question is, how do you completely determine whatever configuration that collection of pieces exists in? You could refer to that as the state of the system, and the question is, how do you determine that state? Well, in quantum computing or in quantum physics, that state is given by a vector, and that's what this bra-ket notation stands for. Or this is technically a ket. That's what this stands for. Whenever you see the straight bar and angle bar or angle bracket, that indicates quantum state. And you can even flip it the other way around, and that means you just take the complex conjugate transpose. So the state is a vector of complex numbers, and the dimension is exponential in the number of qubits. So a qubit is just a particle. It could be an electron, or rather the spin of an electron, or it can be the polarization of a photon, some kind of property of a bit of universe. And whenever you have a collection of k electrons, each electron having a spin, the state of all k electrons is given by a complex vector of 2 to the k elements. And these complex vectors all have length 1. Very important. This is a handy way to write length 1. You take the complex conjugate transpose and multiply it with the original vector. That should sum to 1. This is the analog of saying the probability of all possible events has to sum to 1. So this is describing the state at one point in time. How do you go from the state at one point in time to the state at another point in time? This transformation must preserve the fact that state vectors have length 1. And the mathematical way to write that is to require that the transformation be unitary. Unitary is exactly what describes such transformations. It is the complex analog of orthonormal. So if you take the complex conjugate transpose of a unitary matrix and multiply it with the original matrix, then you get the identity. And these matrices are also exponentially large. So the fact that we deal with exponentially large vectors and exponentially large matrices here, that should give you a bit of an intuition already on where quantum computers derive their computational power from. So what happens when we compose two quantum states? So we have a few qubits here and a few qubits there. What if we put them together? Can we describe the combined system as one big system? And the answer is yes. And we even have a notation for this. The notation was actually already in use before, but it actually perfectly describes what to do with quantum states. We take the Kronecker product, or their tensor product. And what that means, well, let's see what that means as the third option in a logical progression. First, we know the inner product between two vectors is to just take the pairwise products and sum those. Right? Then there's the outer product where the order of the vectors has been swapped. And that's just a matrix of all possible pairwise products. And then the tensor product is the vector of all the entries in that matrix. And we can do the same for matrices, and then if you have a matrix that acts on this vector and a matrix that acts on that vector, and you take the tensor product of those two matrices, it will act on this vector. So that's actually the same thing that you would do for classical probability distributions. If you have 5 bits here with a probability distribution of the possible values, and 5 bits there with a probability distribution of the possible values, the joint probability distribution is described exactly by the tensor product. So, postulate number 4, measurement is taken with respect to an orthogonal basis in which the states live. And after measurement happens, it affects, or rather, as measurement happens, it affects the state, and it fixes the state to one of those measurement vectors with a probability that you can compute by taking the inner product. So this is why the weird bracket notation was invented, because if you imagine that this is a matrix, well, then you have the expectance value. So that's some symbols to reflect the history. So you take the inner product with your ith basis vector and your state, and you take the magnitude of that and you square it. That's the probability of observing the ith basis vector. And obviously, if you have observed that ith basis vector, then the state collapses to that ith basis vector. And all the information on the other possible states has disappeared, sadly. So these vectors all represent bit strings, so there are exponentially many of them. Is that a question? No, you're just stretching. Okay. So let's see a simple example. So we have a single qubit, and its state space is spanned by the basis 0 and 1. And its state is then completely described by a linear combination of 0 and 1, where 0 and 1 are now cats rather than numbers. All right, that's cool. So let's see an operation acting on this state. So we have, hang on, that's the next step. This one is still showing that it's not just any linear combination. It has to be a linear combination such that the state has length 1. All right, so what if we have two qubits that are both set to 0, and we consider the joint system? So that's psi tensor phi, and oftentimes we'll just forget about the tensor product. There are 4 possible observation outcomes. That means we have to define 4 coefficients. Each of them are complex numbers, and their squares have to sum to 1. In this particular case, we know that the state is 0 for psi and 0 for phi. So the amplitude that's associated with 0, 0 has to be 1, and the amplitude associated with all the others has to be 0. Why? Because when we measure, we take the inner product between the basis vectors, and we know that the probability of observing anything else but 0, 0 is 0. So all the probability must come from that coefficient. All right, what happens if we apply this unitary transform? That's an allowable transform. It sends this vector to this vector. You can verify this, but the interesting thing here is that when you measure psi, you get 0 or 1 with 50% probability. And if you measure phi, you'll get 0 or 1 with 50% probability. But you know that the other one will have the exact same value. Even if you send the one electron psi to one edge of the universe and the other electron phi to another edge of the universe, and then you measure them, you will know instantly what the measurement result on the other side of the universe will be. So that's a rather neat property of quantum mechanics. So, can we use this to compute? And the answer is yes. And to illustrate this, I like this slide. This slide is representing diagrammatically what a computation looks like, and time goes down. Time proceeds as you go down the slide, and in this diagram, which are all trees, every point in time has an arrow to every node represents a state, and every state points to the possible states at the next point in time. Now, for deterministic computation, there is no possibility for branching because the computation is deterministic. So if I were to select this state at the bottom and ask what's the probability of reaching that state, well, obviously the probability is 1 because there are no other states. There is no branching. But in the probabilistic case, there is branching, and time goes down, time flows downward, and you can choose a state from the possible end states and ask what's the probability of reaching that state. Well, the probability of reaching that state you can compute by summing the probability of every path that leads there. So you multiply the transition probabilities, and then you sum, then you get a probability. That's the probability of reaching that state. What does it look like in the quantum case? Well, the nodes here don't really represent states anymore, but possible observations. But that's no problem. You can still define the complete list of possible observations at the end of your computation. You can choose one and ask, what's the probability of observing this possible observation? Well, what you do is you take all the amplitudes of all the paths that lead to that observation, and you add them. And then you square them, because you get the probability by squaring the amplitude. But the interesting thing here is that amplitudes can be negative. So this path has a negative sign, and this path has a positive sign. So somehow these paths are interfering, and somehow the probability of following this path and the probability of following that path is greater than the probability of ending in that state. That's called interference. And that's the key property that quantum computers exploit to accelerate computations. So there is a fourth mode of computation called non-deterministic computation, in which the next state isn't really uniquely defined. The only thing that's relevant is, that every possible next state is explored. This is just a mathematical abstraction. It's not realizable. And the whole point, I think, of non-deterministic computation is that every possible end state is reached with probability 1. So I like to use this slide to explain why quantum computers cannot do generic non-deterministic computations, because there's no conservation of probability here. Which is why I think I think no physical process can actually achieve this mode of computation, and it's just a mathematical thing. But I guess that's a conjecture. So I've spoken about the postulates of quantum computation, and they seem very similar to probabilistic computation. So I'd like to cast probabilistic computation into the same postulates, and well, if I fail, then I fail, but let's see how far I can get. A classical state, or rather a classical probability distribution, is fully defined by its vector, which also has exponential size, because this vector is describing a probability distribution, remember? 2 to the k possible values, each with a probability, and all the probabilities sum to 1. Just change the norm. All right? Number 2, a valid transformation preserves the length, which is 1. Well, we have a word for that in mathematics language. It's called the stochastic matrix. Number 3, the composition of two states, probability distributions really, is given by their tensor product. Well, that's just the same without adaptations. Number 4 is a little trickier. Measurement in the quantum case corresponds to sampling in the probabilistic case. Sampling is just, you choose one of the possible observation events and look at the coefficient of that event to determine your probability. And when you've observed that, well, then you know the value of your sample. So you can think of measurement or sampling as taking your probability distribution and concentrating it to one of the samples with non-zero support, in accordance with the probability as defined by the probability distribution. So quantum computation is actually really similar to classical probabilistic computation, and we already know how to think about that. So what's the difference? I'll get to that. So in order to think of quantum computation, you're really not far off by starting with classical probability distributions and admitting continuous transitions as opposed to discrete ones. In particular, the nth root of a computation is always well defined in the quantum case, but not necessarily so in the classical case. So classically, you cannot have half a bit flip. Quantumly, that's no problem. And all the mathematics involved in quantum mechanics derives from this feature, including complex numbers, L2 norm. And if you want to think about quantum algorithms, it's perfectly fine to decompose it into local quantum operations that affect only a few qubits each. I do have a slide on quantum circuits, but that's really a superfluous slide. All right, so what's the key difference between quantum computation and classical probabilistic computation? It's interference, which you may recall from high school physics class. That's the phenomenon when a wavefront hits a wall with two perforations, and each perforation becomes a wave generator in its own right. And when those waves come together, they can either interfere constructively or interfere destructively, depending on whether they are in phase or out phase. And if you look at the amplitude at this point, well, then you have something like this. In some places, the amplitude will cancel, and in some places, they will reinforce. And this is an interference pattern. And quantum computers exploit exactly the same phenomenon. So for instance, let's operate with this unitary matrix on a single qubit that we know was set to 0 initially. So what's the state, or the possible observations at the start? That's just 0. After applying it once, it moves this qubit to the uniform superposition of 0 and 1. And if we were to measure at this point, we're going to see 0 or 1 with equal probability. But we're not going to measure. We're going to apply the same unitary twice. And then we get 1. Why do we get 1? Well, if you draw a diagram of possible observations, well, then you'll notice that this path and that path, they cancel each other. You can compute this from the matrix. The whole point is that one of the paths involves the minus sign, whereas the other does not. And that's why all the paths end on the 1. Destructive interference is the only reason why quantum computers can outperform classical computers. And if you want to design quantum algorithms, what you need to do is you need to engineer interference. So how do you do that? Well, you apply gates, and here are a couple of gates, and they're really not important. So I'll go over this really quickly. You have the controlled NOT gate, which flips the second qubit only if the first one is set. And that gives rise to a unitary matrix like that. You have the Hadamard gate, which sends 0 to the uniform superposition and 1 to the uniform superposition. And you have the T gate, also known as the pi over 8 gate, which just flips the phase of your complex number. Well, it doesn't flip it, it rotates it. And then you have the S gate, which rotates it also, but by a different angle. And you have the controlled unitary gate, which applies the unitary U only if the first qubit is set. And, then there's the measurement, of course. And it's all really not so important, because you can approximate any unitary matrix you can come up with using these gates. And it's far better to just think about how the state transitions, the decomposition into gates. That's possibly necessary if you want to write a paper showing that you really do meet the stated complexity. One more thing that I left off the slide is the controlled NOT gate, or the Toffoli gate, which is just this guy, except you flip the third bit only if the first two are set. And the CC NOT gate is already complete for classical computations. You just take CC NOT and any phase rotation, and then you have a universal gate set. So that was how to think about quantum computation. Let's see Shor's algorithm. And I'm afraid I'm going to skip Grover's algorithm out of time constraints. But if you want to learn more about that, feel free to hit me up later. So Shor's algorithm was the first algorithm to establish a use case for quantum computers that wasn't just merely theoretical, because it solves a real-world problem, namely breaking RSA, and this discrete logarithm problem too, upon which most of elliptic curve cryptography is based. So it reduces the factorization of a product of two large primes to finding the order, and order finding is also what allows you to solve the discrete logarithm problem. So the order is the power to which you raise an element before you get 1. And to find it, you need tools from systems theory and signal processing, which is the Fourier Transform. And there's a quantum analog of the Fourier Transform called the quantum Fourier Transform. So what does the classical Fourier Transform do? It takes a vector of n elements and sends it to another vector of n elements with this weird description involving the roots of unity raised to subsequent powers. And there's a fast algorithm for this, taking time only and log n, which is actually really cool. Quantumly, we can have essentially the same vector up to scale represented by log n qubits, right? Because we encode these complex numbers into the amplitudes of log n qubits. So we have this state, and we want to send it to another state, also of log n qubits, and with the same description. And there is a quantum circuit that does it with the same complexity expression, except in terms of the number of qubits and not in terms of the number of numbers. So that's pretty cool. That's a really, really, really fast Fourier operation on a very large vector, or exponentially large vector. And then there's one more property of Fourier analysis that you need to know about. That's when you have an impulse train, which is a regular sequence of impulses that's not centered at 0, that has an offset from 0, and you take the Fourier domain, Fourier transform of this impulse train, what you get is another impulse train where the period is 1 over the previous period, and this guy does start at 0. That's a very useful property, and it is key in Shor's algorithm. So with this background, let's see Shor's algorithm. So we want to factorize an integer, which is the product of two large primes. And we're going to reduce factorizing to finding the order, meaning that the second we have this order, finding the integers, finding the prime factors is easy. That's just some straightforward number theory. And in order to find this order, we do the following. We have two quantum registers of enough qubits, and we're going to set the first, well, at first they're both set in the uniforms in all zeros, and we're going to apply the Hadamard gate to the first register to set them in the uniform superposition of all bit strings. So if we were to measure the first register at this point, we would get every bit string with the same probability. Now, our state is described exactly by this expression. You sum from I going to 0 to the highest possible value, and I is inside of your ket because it also identifies a possible observation value. So now we apply this function, which is raise x to the power a, where a is the value encoded in the first register. X can be any fixed value. In fact, using 2 will work most of the time. And we just XOR it into the second state. We know into the second register. We know the second register was already set to 0. So as a result of this computation, we will have the same contents in the first register, but x to the I in the second register, which is exactly here. And I omitted writing the coefficients explicitly because that's where it gets a little complicated. So what happens if we measure only the second register? Well, we measure x to the I for a random I. Let's call that y from now on. So after we measure the second register, the first register will collapse, not to a single value, but to some value that is consistent with this observation. Or more precisely, the superposition of all possible offsets of y, which is the discrete log of this guy, that send x to the I to b. This is exactly an impulse train, because we have the discrete log, but after order many steps, we have another exponent that sends x to b. And after order many more steps, we have another exponent that sends x to b. So when you see impulse train, your mind should instantly go to, let's apply the Fourier transform. And that's exactly what the algorithm does. We apply the Fourier transform, and what we get out is another impulse train centered at 0, whose period is 1 over the previous period. And we know the previous period was the order of our number. So after applying the quantum Fourier transform, we can measure A. The Shor's paper describes some post-processing to increase the probability of correctly computing the order, but it should be obvious that it can be obtained from this value already. There is also some extra post-processing involved in showing, because this is a rational number and technically speaking not an integer, but Shor shows that it's the amplitude of integers close to this rational number will be high in exchange. So let's, you can also repeat, and with a couple of iterations you'll get really, really close. So if we were to apply this to a toy example, say x equals 2, 2 always works, and we raise x to the random power encoded in the first register, and then we observe b equals 32. Well, we know the order of 2 is 12. Wait, we don't know that. We observed that, but we'll see that later on. So the first register, after observing b, will have this amplitude distribution. It's an impulse train, but not centered at 0. And after we compute the Fourier transform, we get an impulse train centered at 0, and every 1 over 12 times the width of your Fourier transform, you have a spike. And if you observe one of these spikes, that's basically good enough to observe to obtain the order. So that's how Shor's algorithm works. And it's possible to generalize this because, for instance, it also applies to the discrete logarithm problem, and then there's also Simon's problem. And the way to mathematically formalize this is to say if there is a function f whose input is a group element, and if f, whenever you add a subgroup element to the input of f, you get the same output. That's exactly the description in this box. Whenever you add to the input of f an element from a subgroup, then you get the same output. That defines the hidden subgroup problem, and it's possible to characterize Shor's algorithms as a member of this, but also this interesting predecessor to Shor's algorithm called Simon's algorithm, which solves Simon's problem, which is to find the offset for which a function, an offset R for which a function f of x has the same output of f of x plus r. This actually solves, this can actually be used to break the even-Mansour construction, but you need quantum access. So the even-Mansour construction turns a random permutation into another completely random permutation, or you can even use it to generate block ciphers. You just XOR the key in before and after. And classically, this is really, really robust, and there are a boatload of really good results about this, but quantumly, it's totally broken. And totally broken with the caveat that you do need quantum access to this circuit. So how is it totally broken? Well, you just compute the permutation, which you know applied to the input, and XOR it back in at the end, and then you have a function such that if you add a member of the subgroup, and the subgroup contains only 0 and k, if you add k, you're guaranteed that the output is the same. So from this random looking function, you just added a tiny component, and now you have a function with a very, very strong structure. And you apply Shor's algorithm or Simon's algorithm, but that's basically the same, and you get k out, which is exactly the secret key that's supposed to be known only by the user, not by the adversary. Of course, the big fine print is that it requires quantum access to this primitive, meaning that somehow k, the secret key, would have to be stored on a quantum computer. And most of the time, keys are stored in regular traditional hardware, and it will kill any quantum query coming in. All right, the next slide, I think, is Grover's algorithm. I think this is a good point to cut my presentation short in the interest of time. Are there any questions? No questions. Thank you.